So this lab's going to give you the basic feel of how the BJT transistor works. Kind of similar to what we were talking about in class. What was it? I guess Tuesday last week. I was discussing in class how if we kept increasing the base current, what would happen in that transistor circuit. So this lab will allow you to explore that in a similar fashion, and we can see the transistor switch between the different modes of operation. Let me get some components in Multisim here. By the way, did everybody get their Multisim issues fixed with the updated code from a few weeks ago? All right. Okay, so what I'm going to do here is I'm going to put a base resistor in and then a collector resistor. I'm going to grab a transistor, so that would be in the transistor library. So if you go to group and then transistors, they have all kinds of different transistors in here. So you see the first one says BJT NPN, BJT PNP, BJT COMP is for complementary. These are Darlingtons. Then if you go down further, you see some MOSFETs down here, JFETs, power MOSFETs. So there's a variety of transistors you can grab in Multisim here, but we're using the NPN BJT. So one of the classic transistor part numbers is called the 2N3904. So whenever you think NPN transistor, or whenever someone thinks NPN transistor, they usually are thinking, they're usually thinking of this 2N3904. So it's kind of like the most famous or classic part number of transistor. All right, I'm gonna get some voltage sources. Okay, so we can call this resistor RB. I want to make it a little clearer. So instead of R1, I can change the name to RB. You can just double click on it and then go to the label tab here. Usually it defaults to the value tab when you double click on a component, because usually you're changing values. But if you go over to the label tab, you can also change this is called the reference designator. And that just means the name for that component. So that's RB, and then this would typically be called RC for the collector. Okay, so that's my simple circuit here. The lab has some particular values. So there's a 220K for the base and then a 4.7K for the collector. So I can go back in here and go to value, 220K, and this one 4.7K. And so what this lab is about is you're going to be measuring some voltages and currents, and you're going to create a table of data here. And you're going to kind of cycle through different values of V1. So V1 is the base voltage, the applied voltage to the base here. So there's a separate base supply and a separate collector supply over here. So what we're going to do is we're going to adjust this base supply to different values and see how the voltages and currents in the transistor are changing based on that. So as we know from lecture, you would expect, you would expect as you increase the base voltage, you're basically turning the transistor on more and more. Right? So if you started off at 0 volts on the base, then 0 volts is not enough to turn on the transistor, right? You're not applying any voltage. So that base emitter junction would not be forward biased, and the transistor itself should not conduct as a whole. So we would expect at a base voltage of 0 volts, then there would be no base current, and there would also be no collector current, right? In that situation, the transistor would be acting like an open switch. So if we slowly increase this base voltage, then you're going to get a little bit more and a little bit more base current. And that means that your collector current will also increase, right? Because IC is just beta times IB. So as we increase our base current over here, the collector current on the other side is also going to be increasing. And we know that as the current increases, the voltage drop on this resistor is also going to increase. So at some point, the voltage drop on this resistor will actually equal this source voltage, and then the voltage drop on the transistor itself will drop all the way down to 0. And it can't go anything below 0 though, right? That's what we discussed last time. So the lowest the voltage drop across this transistor can ever go is down to 0 volts. The largest this voltage drop can be is all the way up to whatever your supply voltage is. So in this case, we have a 12 volt supply. So when the transistor is off, we should expect to see 12 volts across the transistor and 0 volts across this resistor. And then as you increase the current more, as you increase the base current, you're increasing the collector current. So the collector current will increase, the voltage across this resistor will increase. And that means that the voltage across the transistor will be decreasing. So if initially you had 12 across the transistor and 0 across the resistor, as you increase the current, the transistor voltage will be going down and the resistor voltage will be going up. And then once the transistor voltage goes all the way down to 0, then it can't drop any further than that, right? You're never going to get a negative voltage there. So the lowest this voltage here could be is 0 volts. So when there's 0 volts across the transistor, that means that there's the full supply voltage across the resistor, right? Because just think about it in a simple KVL loop, right? You have 12 volts applied, and there's 2 places that 12 volts can be, distributed. So there's the transistor voltage drop here, and then there's also the resistor voltage drop. So that 12 volts supply has to be dropped in either entirely on the resistor or entirely on the transistor or some combination of the two. So we're going to see that kind of behavior as we increase the supply voltage. So this lab says to prepare 3 meters, 1 to measure the current for the base, 1 to measure the current for the collector, and then 1 to measure the collector emitter voltage. Okay, so let's set up those meters. So that one for base current, let's use this one for collector current, and one more for the collector emitter voltage. So for my base current, I can just break the loop anywhere here on the base side. I can't break the loop down here because that would also include the collector current, right? Because the base current is flowing down there, but also the collector current is flowing down there. So I would not want to measure this down here. I want to measure it somewhere over on this side where only the base current flows. So I can break any one of these 3 connections to put my meter in series. So how about we just break it right here at the source? And instead of wiring this bend, I'm going to force the current to go through the meter first and then back out to get to the rest of the circuit. So this will represent my base current, IB. And then I'll do the same thing at the top here. So I'm going to force the current to go into my meter. One thing to note here is that if your meter is set, if the leads are flipped on the meter, then you'll get a negative current reading. So the way I have this meter set up over here, the current is flowing into the positive terminal first and then exiting on the negative terminal of the meter. So that would give you a positive reading. So if we want to get similar behavior over here, I have to actually connect the positive to the source here and the negative down to the circuit. So one thing you can do is you can do this thing called the flip horizontal. So if you right click on it, you can flip vertically or flip horizontally. If I flip this horizontally, it basically just means to mirror it horizontally. So now the plus is on the right and the minus is on the left. So that's good for that purpose. So I'll connect my positive of my supply to the positive of the meter. That will make my reading come out as a positive number. And good to go there. So this one will measure collector current. This one will measure base current. Now I want to measure collector emitter voltage. So I'm going to put another meter. I squeeze it in there. Okay. And then the emitter is down here on the bottom. So this is the collector terminal. This is the emitter terminal. So that's the collector emitter voltage. Okay, then I got to set my meters to the correct mode. So this meter is base current. So that's amps. This meter is also a current. So set it to amps. And then this meter down here is voltage. This will be IB, this will be IC, and this will be VCE. Okay, so let's get started here. So let me start this off at 0 volts. I'm starting my base voltage off at 0, and I'm going to run the simulation. All right, so let's see what readings we get. So for my base current, I'm getting a reading of negative 16 picoamps. Right, remember pico is 10 to the minus 12 amps. So pico is very, very small. Picoamps is, basically negligible, 0. So we can say that our base current is roughly 0 amps currently. And what about the collector current? The collector current is very small as well. It's 12 nanoamps. 10 nano is 10 to the minus 9. So basically our base current is 0 and our collector current is 0. These are negligible amounts of current. So that's what we expect to happen. And the transistor is turned off at the moment, right? Because there's no current flowing through it. The base emitter junction is not, there's not sufficient voltage to turn on the base emitter junction. So we have no current flow over here. And since we have no current flow in the base, we also have no current flow in the collector. And in that situation, we would expect to see 12 volts across the transistor because it's behaving like an open circuit there. Let me see if I can pull up the notes from lecture. All right, so remember this discussion about closed switch, open switch stuff. So right now our transistor should be acting like an open switch. So in an open switch, we should have 0 current, and the voltage across the transistor, or the voltage across an open switch, would be the full supply voltage, right? So is that what we're seeing? Yeah, it is pretty much, right? We can approximate this as 0 amps. So there's no current flowing through it. And then there's the full supply voltage across the transistor. So you want to think about the collector and the emitter acting like those two switch terminals. So you see this meter over here is measuring 12 volts. So that means the transistor is dropping the full 12 volts. So if I were to measure across RC, I would get 0 volts, right? There's 0 current here. So there's 0 voltage across it. And all of the voltage is being dropped by the transistor currently. Right, so that should make sense. That's essentially the first point in this table. So you could fill in all of these values and decide what mode of operation that corresponds to. Then we're going to increase our base voltage to 0.5 volts. So let me stop the simulation, change this voltage to 0.5 and rerun it. Okay, 0.5 is not quite enough to turn on the base emitter junction, the diode in there. So we would expect that there's still going to be roughly 0 current and still roughly 0 current in the collector. And then the voltage should be still 12. So you see that it goes, when I increase it from 0 to 0.5, you see it does increase a bit. I don't remember exactly what value it was, but it was like picoamps before. Now it's in nanoamps here. So it did increase, but nanoamps is still, 10 to the minus 9. So it's still a negligible amount of current. The collector current has also increased from nano to microamps now. And that's because I'm getting pretty close to turning this junction on, right? It turns on around 0.5, 0.6. So it starts to turn on. So I'm right at that point where it's starting to turn on, but you can still consider it off for most purposes here. And we see that the voltage across the transistor is 11.993. So the voltage here, still roughly 12, right? To at least 2 decimal points, it's still pretty close to 12. So we haven't really turned the transistor on yet, and we're still seeing roughly 0 base current, 0 collector current, and the full supply voltage across the transistor. So that's what you would expect at a supply voltage of 0.5. So then we're going to just go through and increase this to all the different values listed in this table. Okay, so the next value was 1 volt. So at 1 volt, we should start to see a decent amount of base current, right? So let's see here. We have 1 volt on the base, 220K resistor. We have 1.7 microamps. On the collector, we have 204 microamps, and you see the voltage across the transistor is dropped down to 11 volts now. So the currents have increased, and this voltage across the transistor is starting to come down now. Okay, so that's also what we would expect to happen. You can do a quick check of these figures. Let's see here. So 1.723 microamps, is that the correct value of current? Well, we can do a quick check on that. So think about a KVL loop that goes around here. So if I start here, I'd have a 1 volt supply, 220K resistor, and then a 0.7 drop there. So let's check that value. So if I do plus 1 volt minus the base current times 220K minus 0.7 volts for the base emitter drop, that has to equal 0. And then IB would be 1 minus 0.7 divided by 220K. So let's see what that is. 1 minus 0.7 is 0.3, so 0.3 over 220K. About 1.36 microamps is what we should be getting. Okay, so we see the current here is a bit higher. and that's because we're down at a pretty low supply voltage here. So the measured value here is 1.7. The calculated value is 1.36. So that's a pretty significant error, but I think you can see that it probably depends a lot on this 0.7, right? We know that if you're barely turning the transistor on, then the voltage drop is not going to be, the voltage drop will be closer to the 0.5, 0.6 area. And you can see if I change this calculation, so this was all assuming, this is assuming that VBE is equal to 0.7, right? But if we had changed VBE to be like 0.6 or 0.5 or something like that, something a little bit lower, what that would do is make this part being subtracted, it'll be smaller. So the overall result will be larger. So if I tried it with like 0.6, for example, then this would be 0.4 instead of 0.3. And you can see I'm getting much closer to what I measure, 1.81. So it looks like the transistor in the simulation, it's dropping about 0.6 something volts, 0.62 maybe. So that's a perfectly reasonable answer. So even though we didn't get, even though by assuming 0.7, our answer is pretty inaccurate, we can easily see why, right? Because we're just barely turning the transistor on. So since we're barely turning it on, you know, from the diode, you know, whenever we have that diode IV characteristic curve, looks something like this, right? 0.7 would be somewhere about here. So right now we're probably operating closer to something like that, right? It's just barely starting to turn on. So the voltage is closer to probably 0.6. That's what we're seeing right now. Okay, and then we also see that the collector current is increasing pretty good now, right? It's hundreds of microamps. So we can do a quick check here. We have a base current of 1.7 and we have a collector current of 205. So remember, these are supposed to be related by that factor beta. So IC is supposed to equal beta times IB. So we can get a rough idea of what is beta here. Now, let me just fill this in. This was about 1.8 microamps. And we had a measured value was 1.723. Okay, so now I wanted to look at beta. All right, so we know this relationship IC is equal to beta times IB, and we can actually just solve that for beta. So if we measured IC and we measured IB, then we can just solve that for beta to figure out what that value is. So beta would just be IC divided by IB, and I think we measured 204. Let's just call that 205, roughly 205 microamps divided by 1.7, was it? 1.723. We'll take those two values, divide them. 205 divided by 1.723. I'm just drop the micros because it's micro divided by micro, so that'll cancel out. I'm getting a beta of about 119, let's say. So this would be like a measured beta, right? Because this value came from a measurement of collector current and a measurement of base current. So this is effectively a measurement of beta. So apparently in this simulation, the beta of the transistor is currently about 119. And this number will actually change a little bit as you increase or decrease voltages and currents. But it can be thought of to kind of be a minimum value. We'll take a look at a data sheet in a bit. All right, so let's go. So let's just keep increasing this voltage. Let's try some higher levels. Let's go to 3 volts. See what we get. So at 3 volts, getting a base current of 10 microamps, a collector current is now in the milliamps, right? It used to be in the microamps. It used to be like a couple hundred microamps. So the collector current has increased quite a bit. And you see the collector emitter voltage now is dropping to less than half of the supply, right? The supply is 12 and my collector emitter voltage is 4.7. So that means there's 4.7 volts across the transistor. There must be, 12 minus 4.7 across this resistor. So what is that? That's like a 7.3, right? So there's about 7.3 across the resistor at the moment and 4.7 across the transistor, right? And those two voltages again have to add up to 12. So it can either be all dropped across the transistor or all across the resistor or some combination thereof. Okay, so let's see if this makes any sense. So let's just run another sample calculation here. So 3 volts, 220K, and then we have our base emitter junction. So for base voltage, I think it was called V1. For V1 equal to 3 volts, our KVL loop should be plus 3 minus the base current times 220K minus the base emitter voltage, which is 0.7, has to equal 0. So 3 minus 0.7 over 220K, 2.3 over 220K, 10.45 microamps. You can see we're getting something very close to that. Okay, so that came out pretty good. And then let's see if, what's it called? Let's see about the beta. Beta is IC divided by IB here. And we have IC is 1.551 milliamps and 10.45 microamps. So from inspection, it looks like it's going to be about maybe 150. I got to be careful about the units here because these are not both in micro anymore. So one is in milliamps and one is in micro. So I can just do A and S for my previous answer because that was the last thing I input. So I'm getting a beta now of about 148. So my measured beta is increasing a bit. So you see the beta was about 120 over here. Now it's about closer to 150 as I turn it on a little more. So we think about beta as being roughly constant, but in practice, it really isn't. It really depends on exactly how much current you have applied to the transistor. But we're going to learn some ways to design circuits later where they become kind of insensitive to changes in beta. So yeah, like I said, in theory, we often analyze a transistor circuit as if the beta value is constant, but that's rarely going to be the case. So the beta value does fluctuate within a range. So as long as we know what the minimum of that range is and what the maximum of that range is, that's usually good enough to design a circuit that will work well under all possibilities. When we learn some other techniques in a little bit, how to make your design less sensitive to beta. So this design we're looking at right now is very sensitive to beta, but we'll look at some other designs later that will be insensitive to changes in beta. All right, so yeah, our beta value is roughly 150 at that 3 volt point. It was maybe 120. I think it was at 1 volt. And so what we're seeing as we increase through this table is we're seeing base currents are going up, right? Base currents are going up because we're increasing our voltage that we're applying to the base. So V1 is a supply that's connected directly to the base. So as we increase this voltage, we're increasing the base current. So base current's increasing over here. And since the collector current is just beta times the base current, we would expect the collector current to also increase as we go down. And then VCE is the voltage across the transistor from collector to emitter. And we saw the very first point, VCE was equal to our supply voltage of 12 volts. And then as we increase down this column, the collector emitter voltage is going to start off at 12, start off at our supply voltage, and it's going to decrease as we go down, right? Because we're turning the transistor on more and more. So when the transistor is fully off, it looks like an open switch, so it drops the full supply voltage. And when the transistor is fully on, then it's going to look like a closed switch, which means VCE will go down to 0. So initially it's 12 here, and then it'll approach 0 as we go down this table. So let's see if we can get to some higher levels. I'm not doing all the points, I'm just jumping. So let's try the last point, I think was 7. Let's try that one. Okay, so at 7 volts says my base current is 28 micro. My collector current is 2.5. And the collector emitter voltage is 151 millivolts. Actually, let me backtrack a little bit. Let's go to a slightly lower voltage. All right, so I want to look at this one. At 4 volts applied to the base here, you see the collector emitter voltage is about 1.5. So the transistor is only dropping 1.5. And since we have a 12 volt supply, that means there's 10.5 volts up here across the resistor. So the transistor is getting really close to entering that saturation mode here. The voltage across it is very low. And we know that as the voltage reaches 0 over here, that means it's acting like a closed switch, or that's the saturation mode. So we're getting pretty close to that. you can see the voltage is 1.5 here. Now watch what happens if I increase it to 5. Oops. So it was 1.5. Keep that in mind. Now it drops down to 191 millivolts. So that's 0.2 volts roughly. Okay, now let me increase it to 6. You see it only changed from 0.2 millivolts to not 0.2 millivolts, 0.2 volts to 0.16 volts. Right, very little change right here now. Even though I increased this by another whole other volt, this hardly changed at all. So why is that? Well, because we're getting really close to saturation now. And actually, the practical behavior of the transistor in saturation mode is it doesn't really reach a true 0 volts, but it gets very small. So many people would approximate the drop on a transistor in saturation. They would approximate that as 0.2 or 0.1 volts. And you can see that's exactly what we're getting here. We're getting about 0.16 volts. So the voltage over here can never truly go to 0, but it can get reasonably close. So we can say that this is approximately 0. So think about this resistor here. This resistor is not getting the full 12 volts, but the resistor is getting pretty close there, right? It's getting 11.83. The resistor would be getting 11.83 volts. So if this wasn't a resistor and this was instead like a motor or something that you were controlling, like let's say you wanted to have a motor up here and you switch it off and on with this transistor, that would be reasonable. That would be acceptable, right? The motor would not be getting the full 12 volts, but it would be getting darn close to it. 11.83 is close enough for most practical purposes here. So this transistor is doing its job as far as acting like a closed switch, but it's not a perfect ideal switch, right? There is a little bit of voltage drop on the transistor. So it's about 160 millivolts in this case. And as I continue to turn the transistor on more and more, it might go down a little bit, but you're not going to see it go down to 0. So you see it went from, at 5 volts, I had about 190 millivolts. And then at 6 volts here, I had 160. And then at 7 volts, I have 150. So it hardly is dropping now. And if I keep increasing this, let's say to like 10, it's jumped by a lot. We should not see a big change here. It's going down, but not very much. It's kind of slowly approaching 0, but it's never going to get to 0. So the voltage drop is kind of not changing anymore here. So that's telling you that you're in saturation mode. Whenever you increase the base current or increase this applied base voltage and these values don't really change, that means that you're in saturation mode and you can't give it, you can't get any more current out of it, basically. Let's kind of look at the other meter now. Same thing, but let's look at the other meter. So that was the discussion of VCE. Let's take a look at the current. So let's compare these two currents. Maybe put these side by side. And let's compare these two currents. So right now at 5 volts, I have roughly 20 microamps here and 2.5 milliamps there. Okay. And we're really close to getting saturation mode. We're pretty much barely inside of saturation mode now. So if I increase this base voltage, that should increase the base current, right? And then if beta is whatever value it is, 120 or 150, that should mean that the collector current would also increase. But we see here that the base current did increase when I changed my supply, but this value didn't really change, right? 2.5 is still 2.5. So my base current increased, but my collector current decreased, or didn't decrease, but it just didn't increase. Right? This stayed roughly the same, even though this increased on the left. So let's try going to another voltage, even higher. Right, now we have 28 here instead of 20, and this is still 2.5. So yeah, it did go up a tiny, tiny bit, but it's not really changing much at all, right? So that's another way you can tell that you're in saturation, is that your collector current can no longer increase. So base current is increasing just fine, but the collector current is no longer tracking it, right? So we said that, the collector current is supposed to be beta times the base current. So if the base current increases by 10%, the collector current should also increase by 10%, but we're not seeing that behavior at all. We're seeing the collector current stay roughly the same as the base current increases. So that's indicative of saturation mode. So in this table, you'd expect in some region you're going to get, cutoff mode. In some region you're going to get saturation mode, and in some region, anywhere in between those two extremes, you're going to have linear mode of operation. Okay, so using this data, calculate beta. Yeah, so that's what I've been doing. So I probably should have already done it in here, but you can add another, you're going to insert column to the right or something, and then put like a calculated beta value here. You can put a calculated beta value. So all you have to do is take a IC divided by IB. So that's probably best done in like Excel or something. Just take the collector current divided by the base current, and then you can have a beta for each of these data points. And again, the beta value is going to change, and especially over here at saturation mode, because think about it, the collector current is no longer increasing. So the numerator of that expression is no longer changing, but the denominator is still increasing. So beta should be, roughly 120 to 150 in probably this region here. But once you get in close to saturation down here, then you're going to see that the beta value is going to be dropping, right? Because collector current is staying the same, but the base current is increasing. So when basically the denominator is going to be increasing while the numerator stays the same. So you'd expect that the beta value would be dropping in that case. All right. So I think that's all for this lab here. So this is just to give you a feel for how the BJT operates as I change some parameters. All right, so we'll call it a day here.